so I'm going to give this talk on perceptual vector quantization for video coding. So all of the actual inventive work in this talk was done by Jean-Marc, but he couldn't be here today. I think my only real contribution is saying, please note, don't use Gibbons rotations, use a Householder reflection. But you'll see why in a moment. So what are we trying to do here? So perceptual vector quantization is an attempt to apply gain shape quantization to video coding. And so the idea is that we want to separate the amount of gain or contrast that we have present in our transform coefficients from how that contrast, how that energy is distributed in the spectrum that we're trying to compress. And there are a number of reasons that we want to do this. So one is that it makes it much easier to explicitly preserve contrast. Because we're going to actually code the gain, which represents how much energy there is or how much contrast there is in a particular region. Because we code that explicitly, we can make sure that we get it right. Whereas if you're doing something like scalar quantization, where you have a bunch of transform coefficients and you quantize each one individually, it's very easy for you to lose all the energy in small coefficients because you don't have enough bits to code each one individually. It's potentially a better representation of the coefficients. So this idea that gain is a meaningful parameter in some sense, right? Whereas a bunch of individual coefficient values may mean like, okay, you have some energy at this particular frequency in this particular direction, but is not, by itself doesn't have a lot of meaning. Whereas, things like there's a lot of activity in this region is something that is much more spatially correlated in an image. It also gives us this idea of activity masking for free. And so I'll talk about that a little bit in more detail later, but the idea is that we'll be able to throw away information in regions of high contrast because the relative error will be smaller in those regions. And the actual thing we need to do to decide how much information we can throw away is this gain parameter, which we're explicitly encoding. So we don't have to code any extra side information for that, whereas as other formats do. All right, so we'll start off with the simple case. So this is PVQ without a predictor. So the gain just gets scalar quantized, so that's just it's just an explicit value. For the shape, we're going to use a codebook that was actually taken from the pyramid vector quantization codebook of Fisher. Which basically the idea is that we want to place k unit pulses in n dimensions. So we manage, if you have an n-dimensional vector and I have k unit pulses that I can allocate one at a time. So I can place one in one dimension and two in another dimension and so on until I've used up k of them. They can either be positive or negative, but all the ones in the same dimension have to point in the same direction. And another way of writing this down is I just have a vector of integers. When I sum the absolute value of all my integers, I'm going to get k at the end. So that defines the kind of vectors that can exist in this codebook. The important part of this is that this only has n-1 degrees of freedom for an n-dimensional coefficient. And so there are lots of reasons that people normally want to use vector quantization. We talk about the memory advantage and the space filling advantage and all those things. We're not actually using vector quantization for any of that. We just want to eliminate the redundancy of the fact that we've already encoded the gain, which is 1 degree of freedom. And now we want to encode the other, the shape, which is n coefficients, using only n-1 degrees of freedom. We use this vector code to do that. So the gain itself represents the amount of energy, so the L2 norm of the vector. And this codebook, it preserves L1 norm, because we're summing absolute values, right? So in order to correct for that, we just take all of our code words and normalize them to have unit norm. And so that is what differs from the original pyramid vector quantization in what we're doing. The actual size of the codebook is determined by this parameter k, and we can just derive that implicitly from the gain based on knowing how finely spaced we want the code words to be based on the actual gain, which will tell us the radius of our sphere. So what do these codebooks look like? So this is an example for n equals 3. In practice, we use n much larger than that, but I don't have the ability to put that on a slide. But this just shows how the points are distributed on the sphere for various different Ks. They're not uniform, and you can prove that that's basically impossible to do in 3 dimensions. But because our coefficients are somewhat close to Laplacian distributed, the fact that we have points more closely clustered at the poles of these spheres is actually a good thing. So now we want to do this using prediction, right? Because we're doing video coding, and most of our gain in video compression comes from having temporal predictions from the frame before us, right? So we can do what normal codecs do, where you subtract the prediction from the thing you want to code and code a residual. But if we do that using the PVQ that, as just described, then our gain no longer does the thing we want, right? It's not representing the contrast, it's representing some amount of how much changed here, which is something else entirely. But we still really want to use predictors, right? Because you can't do video coding without having good prediction. So predicting the gain itself is easy, right? Because I have a predictor, and I can compute its gain, and I can then code my gain relative to that. So there's no problems there. The problem comes when now I want to predict the shape. And so we had done a bunch of work with this previously in the Opus audio codec, where we were trying to warp the code book on the surface of a sphere and change probability distributions around, and that all got really complicated, and we eventually ripped it all out because it didn't help very well. But finally we came up with this idea, unfortunately after we finished that codec, to just transform the space to make the problem easier. So what do I mean by that? So we can start off, this is just a 2D projection of a higher dimensional example, but we have an input vector, and we have a prediction vector, and both the encoder and the decoder know what the prediction vector is. So they can use it to compute a householder reflection that maps the prediction onto one of my axes. In particular, we always pick the axis where the coefficient of that vector has the largest magnitude, just for numerical reasons. So we reflect both the prediction and the input, and now I can compute and code the angle between these two things. And so what this angle is doing is really saying, how close are you to the prediction? And because that's now separated into its own individual parameter, I can entropy code it separately, I can give it its own probability distribution, and this makes it much more easy to to make it cheap to code things that are close to the predictor and expensive to code things that are far, right? It's very common in one of these bands, like that entire high energy band might have nothing in it, just because that's what the DCT does, right? It makes things sparse in frequency domain. So our current approach is that we just actually code an extra flag that's called no ref, which means don't use a reference, and that's jointly signaled with gain and theta. So, given that, we can now talk about how we do activity masking. So the idea of activity masking is that we want to have better quantization resolution in flat areas, right? And so most codecs require this to be explicitly signaled, so they'll modify the quantizer on a macro block by macro block basis and say, in these flat areas use a finer quantizer, in these active areas use a coarser quantizer. But because we know what the gain is, we can do this implicitly, because that's exactly the piece of information we need to do to decide what quantizer to use, and we can do it on a band-by-band basis. We actually tried doing it on a coarser basis than that, basically try to account for interband masking, and that wound up being very complicated and actually hurt performance. So we ripped all that out. But the way we do this is we just use a non-uniform quantization of the gain. So smaller gain values have smaller quantization step sizes, and larger gain values have larger quantization step sizes. And then we change the function that we use to compute k, the size of our code book, from the gain. So that when the gain is smaller, then we bias towards having larger k's, and when the gain is larger, then we bias towards having smaller k's. And the details of how all that works is described in the paper, but I don't have time to go through that here. So hopefully this comes out to the people in the back. But this is an example image coded without activity masking. and the same image coded with activity masking. So these two are the same size, but if you particularly look in the background of the trees, you can see the one with activity masking has a lot more detail, it's a lot less washed out. So I'm not sure how clear that comes out to you guys, but we did some tests to verify that this is performing well. So this is just PVQ versus a traditional scalar quantizer measured with PSNR across 18 different video clips. And you can see there we get a fairly significant performance improvement. And then we also did a test where we compare PVQ with activity masking to PVQ without activity masking. And you would expect that to degrade PSNR, and it does, but we used one of these more perceptual-based metrics, in this particular case, fast SSIM, which is a fast implementation of multi-scale SSIM. And that also shows a large performance improvement. So there are a number of places that we plan to go from here. So one is we can do better entropy coding. So we're actually not taking any advantage of the fact that we expect these gains to be highly correlated between, in different regions of the image, or even across bands in the same region. We're doing very approximate rate distortion optimization. So, you can't actually produce a rate for a vector until you know what the whole vector is. So if the normal way that we actually do the quantization search is that you place one of these pulses at a time, and at the end of that, when you've placed all of your pulses, then you can compute a rate for the thing by actually going through and coding all of that. But you want to have an estimate of what your rate will be at each decision to place a pulse, and so we use very approximate rate estimates for that at the moment. There's some more far out things like trying to actually inject noise into places instead of coding what it is, and trying to account for motion blur. And then all of this stuff is currently implemented in floating point, and of course for real codec you'd have to do this in fixed point and all that kind of stuff. So there's plenty of tuning work that can be done on this. But sort of summarize that we have a website where you can go read more about this. There's a nice demo that has a bunch of fancy images. The code is all in Git for anyone who wants to go look at it. And you can always reach us on IRC or on a mailing list if you want to know more. So, are there any questions?